Hi, everybody. Today we're going to look at the second part of this chapter, which is actually doing some numerical calculations with simple harmonic motion. Now, a quick reminder before we get started, what's the single requirement for simple harmonic motion? The restoring force has to be proportional to the displacement. And if you do that, then the frequency and or period of the oscillation doesn't change. So, for example, guitars are simple harmonic oscillators. They exhibit simple harmonic motion. Even as the guitar string's amplitude gets smaller, that's the distance it vibrates, the frequency stays the same. All musical instruments are simple harmonic oscillators. But now let's talk about a little bit about the numbers about it. So first of all, a couple definitions. Amplitude is the maximum displacement from equilibrium, and it's represented by the symbol A. And it's usually measured either in meters if you're talking about like a mass spring oscillator, or it could be measured in theta if you're talking about an angle. In this case, the amplitude of this boat ride would be the angle between its equilibrium position, which is straight down, and either one of the endpoints. That amplitude should be the same on both sides. The next thing we're going to talk about is the period. That's the time it takes for one complete cycle of motion. What's a complete cycle of motion? Well, that would be the time required for it to return to its original position. So, for example, this boat, when it swings from this position all the way to the other side and then back again, is one complete cycle or one complete oscillation. And that time that it takes it to do that is what we call the period, represented by capital T. It's the same capital T that you talked about in circular motion, the time for one complete circular motion. So here's a quick example. Let's say this boat took a total of 10 seconds to complete one oscillation, one complete cycle back and forth. Means 5 seconds over, 5 seconds back. What we would say then is that the period is 10 seconds. Again, representing that with a capital T. The other thing we want to talk about besides period is the concept of frequency. Frequency is the number of cycles or oscillations completed per unit of time. And typically that unit of time is a second. If we use seconds for the time interval, the unit ends up being number of oscillations per second. And so the units are 1 over seconds or seconds to the negative 1 power. But because it's actually frequency is used so frequently in physics, it's given its own special unit, the hertz. So for example, your computer CPU oscillates in the gigahertz range. That's billions of cycles per second. Radio stations are usually in megahertz on your radio dial. That's millions of oscillations per second, or kilohertz, thousands of oscillations per second. Period and frequency are inversely related. Frequency is equal to 1 over the period, or period is equal to 1 over the frequency. These are the relationships between those two. So take a quick look at this one. If the swinging boat on the previous problem completed one oscillation or one complete back and forth every 20 seconds, what would be its frequency? Well, period would be 20 seconds, and if we do the reciprocal of that, 1 over 20 is 0.05 hertz. So that would be its frequency. Moving on, let's take a look at another example. In this case, pretend that the illustration here is going a little bit faster. Let's say it completes 8 cycles or 8 complete back and forths every second. The question is what's the period, what's the frequency? Well, what does this 8 cycles per second mean? Well, that's the number of oscillations per second, and by definition, that is the frequency. So we would say its frequency is 8 oscillations per second, or 8 hertz. How do we calculate the period? Well, remember, period is the reciprocal of the frequency, so I can use this. And solving this, the frequency is 8 hertz, and if we solve it, it ends up being 1/8 of a second, or 0.125 seconds. That's the amount of time required to complete one complete back and forth. What's the frequency? Well, we actually already knew that from up here. It is just 8 hertz. So frequency measured in hertz, period measured in seconds. And these two quantities are reciprocals of each other. What affects the frequency or the period of a mass spring oscillator? The heavier the mass, the longer it takes to go back and forth. There's more inertia. And the stiffer the spring, the less time it takes to complete one cycle. Generally speaking, here is our mathematical definition. The period of a mass spring oscillator is equal to, so T's period, 2 times pi, that's a constant, times the square root of the mass, that's the mass that's oscillating back and forth, divided by the spring constant, K. And again, remember, each spring has its own unique spring constant. And so you just have to plug in numbers to get the period. Sorry, it's going to take me longer to write this than it's worth. I'll just write the spring constant. So a couple of quick examples here. A car actually has 4 springs, each one of them with some spring constant, K, and usually the 4 springs in a car are identical. There's a few that are not, but the springs just basically a big coil. They're very stiff springs. So let's take a look at this one. A body of a 1,275 kilogram car is supported on a frame by those 4 springs. 2 people are riding in the car with a combined mass of that. When driven over a pothole in the road, the frame vibrates with a period of that, 0.84 seconds. For the first few seconds, the vibration approximates simple harmonic motion. A, find the combined spring constant of the 4 springs of the car. B, find the spring constant for just one spring. All right, so let's do A first. What equation are we using? This one right here. Plugging in what we know. The period we're given as this many seconds, so we'll put that in here. And then the mass is both the mass of the car plus the mass of the people. So we're going to put that up there, the combined mass of them right here. Adding those together gives us that. And now I'm going to divide both sides of this equation by 2 pi. Why? I want to try and get the square root by itself. It'll make it easier to solve. So I get this. How do I get rid of the square root? Well, I'm going to take this quantity and square both sides. And I'm going to convert this into decimal real quick. So 0.84 divided by 2 pi, and then squaring it gives me this. And then I lose the square root on this side. So this divided by 2 pi squared is this number, equals that. How do I solve for k? Well, I end up multiplying both sides by k first, and then dividing both sides by 0.669. And you'll get that the spring constant for all 4 springs together is 2140 to 3 sig figs. The second part of this question, B, so I can draw a line here, sort of separate these two, asks, all right, so we've got that now. What's the spring constant for just one of the 4 springs? Well, if you remember from last time, when you have springs in parallel, that is side by side, the total spring constant, in this case all of them, would be equal to the spring constant of the first one plus the spring constant of the second spring plus the spring constant of the third spring plus the spring constant of the fourth spring. You get the idea here. In other words, this whole side on this thing is simply equal to 4k, where k is the spring constant for one of these. So how can I solve this? If I want to figure out, if we know the overall, this all one here is equal to 4k, for one of the springs then it would be equal to this constant over here divided by 4. And if we solve this real quick, we'll discover that the spring constant for just one of the springs is 1/4 of that total we found over here, or about 534 Newton meters. And you should say, okay, that's pretty good. So it's not too bad. It's a lot of number crunching, a lot of algebra, but nothing too horrible. What about pendulums? Well, it turns out for small amplitudes, and you're like, wait, what's a small amplitude? Um, Say that the angle that you deflect it is less than or equal to about 10 degrees. Actually, I'll go to 15 degrees. That means if you've got a pendulum that's normally like this, here's the mass on the end, you can move it all the way over here until the angle reaches about 15 degrees, and this will still exhibit simple harmonic motion. If you go much beyond that, something weird happens, and it turns out the period does actually get affected by the amplitude. The greater you swing it out, the greater the period gets, and that's not what we want with the simple harmonic oscillator. We want these things to actually have the same frequency or period. It does, however, is affected by the length. Here is the equation for pendulums, where T is the period, L is the length of the pendulum, and G is the acceleration of gravity, which normally we just make 10 or 9.8. But to be a little bit more precise in this chapter, I'll actually go to 3 sig figs and use 9.81 if you're on the surface of the Earth, meters squared. I know it varies a little bit, but not a lot. We'll talk more about that in a second. So, a couple quick examples. What you have over here in the illustration, if you've ever been to a science museum, they oftentimes have these. This is called the Foucault's pendulum. And it's one of the proofs that the Earth rotates. Even as the pendulum swings back and forth, it'll knock over these little, in this case, little pieces that are standing up. And it's because the Earth is rotating underneath it. Let's say this thing has a period of 12.2 seconds. What's the length of the pendulum? Well, using the same equation, we're going to do a little plug and chug. Here's our period, 12.2 from up above. And dividing both sides by 2 pi, again, just to get the radical by itself, we get that. And now I'm going to divide and square both sides. So if you take 12.2 divided by 2 pi and then square it, you'll end up with 3.77 equals L over 9.81. And if you solve it then, you'll discover that this pendulum over here is about 37 meters tall. That's about 12 stories. That's a crazy long pendulum. But this pendulum is taking about 6.1 seconds to go across this once, and it takes about 6.1 to go back again. One of the most common pendulums you ever see is usually in a grandfather or grandmother clock. It turns out, in a grandfather or grandmother clock, the time it takes the pendulum to go there and back is a total of 2 seconds. In other words, it's 1 second across one way and then another second to come back. So 1 second there, 1 second back. Total of 2 seconds for one complete oscillation. What's the length? We're going to do very much the same thing. In this case, the period is 2 seconds. We're going to plug that in right here. Divide both sides by 2 pi. If you take this quantity, divide it, and then square it, we're going to square both sides of this. We'll get that. And then multiplying it through, you get about that. And for first order approximations, it's about 1 meter. So the pendulum lengths in a grandfather or grandmother clock, this length right here is always about 1 meter. A little bit less, but not much. So all grandfather or grandmother clocks have the same length pendulums, even though they may not look like it. At this point, some of you are saying, well, wait a second. We've got a clock on our wall that the pendulum is definitely not 1 meter long. Yeah, cuckoo clocks. They actually have a period of about 1 second. They have a much shorter pendulum. So there and back only takes 1 second. So a half a second each way. So a half a second over, a half a second back. What's the length of this pendulum? Well, very quickly doing it, in this case, the period 1 second gets put over here. Dividing both sides by 2 pi gives us that. Dividing the 1 over 2 pi and squaring both sides gives us that. And you'll get the length here is about that. Or I always like thinking it's about 25 centimeters. About a fourth as long as a grandfather or grandmother clock. Much, much faster oscillation. Now a thought problem. What if you took a cuckoo clock that has a period of 1 second on Earth? what'll happen to its period if you take it to the surface of the moon? You're like, oh, cuckoo clocks don't work on the moon. Actually, the pendulum will still swing. You won't hear the cuckoo actually make the cuckoo sound, but on that, it'll actually still work. What'll happen to its period? If you're watching this in the video, pause it for a second before we talk about it. I want you to guess, does its period get longer or shorter? Pause now. All right. Hopefully you realize we have to use this equation again. What happens? On the moon, g is smaller. What does that do to this fraction inside here? Well, if you make the denominator of a fraction smaller, what happens to the entire fraction? The entire fraction gets larger, which means when we take the square root of this, this will get larger. In other words, longer as well. What's going to happen to our cuckoo clock? It's going to take longer for the pendulum to go back and forth, which means what's going to happen? Our cuckoo clock, so first of all, the answer is the period gets longer. It's going to take longer for this to go back and forth, which means our cuckoo clock will still work. It's just going to run much slower. The pendulum's going to take longer to go back and forth. Time will seem to run slower on the clock. In reality, time's still running the same speed. It's just pendulum clocks don't work. By the way, just a side note, the astronauts, the Apollo astronauts, did not have digital watches. What kind of watches did they use? They used just wind-up wristwatches. It turns out wristwatches, we'll talk about this later, are just simple mass spring oscillators. I'll show it in the next image, actually. And so, believe it or not, wind-up watches that just had a spring and mass inside did keep perfect time on the moon, even though gravity was different. Gravity affects pendulums. It doesn't affect mass spring oscillators. And this may actually give you a hint for this slide. I need to quick explain this one. Prospectors for gold in the 1800s would take a pendulum clock and a pocket watch with them. And then they would synchronize the two clocks before they went to bed. In the morning, they would compare the times on the two clocks and decide if they should stake a claim. Explain how in the world this actually worked. Now, real quick on this one, pocket watch is a mass spring oscillator. This is what it looks like inside. And so it's using this formula. And the pendulum clock, the grandfather clock, is using this equation. You're like, wait, how in the world could you detect gold with this? I'll give you one hint. Gold is very dense, almost the same density as lead. In other words, it's got a large amount of mass per unit volume. Could you please pause the video if you're watching this? And I want you to argue this one out for a moment before I give you the answer. So pause now. Welcome back. How in the world did this work? The answer is if there was a gold deposit under the ground, it meant that that is a much more dense material. There is more matter present here. And so if you're camping up above this, what happened? G might be a little bit larger than normal. It actually could be greater than 9.81 immediately above this thing. What would that do to your clocks? Well, your pocket watch would not be affected. Doesn't affect mass or spring constant. But if G was bigger, it would make this expression smaller. And so the period would get smaller. In other words, your pendulum clock would take less time to complete one oscillation. What would happen? The pendulum in the pendulum clock would swing faster back and forth, and so this would actually gain time. It would run fast. And so in the morning, if you woke up and your pendulum clock was ahead of your pocket watch, you would say, aha, I must be above something that increased gravity at this point. And yes, you would stake a claim. You're like, great, we can go out and actually do this. Well, before you do that, I should quick warn you on this one. This would run fast if there was gold below you, but it also could just be an iron deposit, not worth so much, or a copper deposit, or just about any dense metal below you could increase G. And so it wouldn't always necessarily guarantee you to find gold, but at least it gave you a good hint that this might actually work. Finally, a thought problem, or not finally, but we're getting close to the end. You're sitting on a swing, a friend gives you a small push, and you oscillate back and forth with a period T1. Now you decide to stand up on this thing. So now if you're standing and then you swing back and forth, would your period stay the same? We'll call this one T2. So the options are here. Which one's the right one? Do the periods stay the same? You're like, yeah, because the length of the swing hasn't changed. Or are the two periods different from each other? If you would please pause the video, think about it for a brief moment before you continue. Welcome back. There's one thing we haven't talked about with pendulums yet, but a pendulum's length is actually from the pivot point to the center of mass of the object that's swinging. So what's happening in this case? The true length of this pendulum is from the pivot point down to here, and over here, it's much shorter. If you look at the equation, if you make L smaller, the period is going to get smaller. So what's going to be true? T2, where the shorter length, has to be a smaller period than T1. Correct answer on this one? It's going to take longer to swing back and forth if you're sitting than if you're standing. All right, we're at a brain break. All of these 7-letter words start with the letter P and end with the letter M. You've got to de-scramble the letters over here to fill in the blanks to figure out what they are. I think this is one of the easier brain breaks. So if you're working on this by yourself, pause the video right now before you continue on. All right, welcome back. Hopefully you got the answers on this one. The 5 words: phantom, perform or preform, problem, premium, and pilgrim. All right, we're to our homework tonight. Tonight you have worksheet 2 and a couple of textbook problems. I just want to quickly do one of the textbook problems, this one right over here, with you before I let you work on the rest. They give you a data table up here and says sketch a graph of force on the y-axis versus displacement on the x-axis using the data table above. But you're like, wait a second, we're missing some data. If you haven't already figured, this is a simple mass, force mass thing. And if you remember for springs, the greater the force you apply, the greater distance that it stretches. In fact, it's given by Hooke's law. Excuse my F here is not quite very pretty. The restoring force is equal to negative K times the displacement. And so even though they didn't give us the rest of the data on this data table, we should be able to figure out these 3. Notice that when you stretch it 0.1 meters, the force is 12. When you do this, 0.2 is 24. You might recognize, hey, it's increasing by 12 newtons each time we increase it by 0.1 meters. So whatever are the 3? Well, 36, adding 12, 48, and 60. And now that I have both our displacement and the force, we can graph this. Our displacement goes from 0 to 0.5. So I'm going to spread those out here. These are in meters. And our force goes from 0 to 60. So I'm going to work on that as well. And this is in newtons. And I'm going to go every unit here is going to be 4 newtons. If we graph our data, 0.1 is 12 newtons. That's going to be exactly right here on this line. 0.2, whoops, going backwards. 0.2 is 24. That's exactly on this line. 0.3 is 36. That's right on this line. 0.4 is 48, that's right on this line, and 0.5 is 60, right on this line. If we do a best fit line, it's actually a perfectly straight line, even though my dots are in exactly right spot. But then down here in part E, it says calculate the slope. How do you calculate slope? Well, if you might remember, slope is rise over run. So in this case, the rise, I'll write this out real quick. The rise is our force. How much does the force increase? Over the run, how much does our displacement decrease? And you could use any of the points on here. I'm actually going to use 0, 0 down here, and this last point right here, because all of them are perfectly collinear. Solving this, slope is rise over run, in this case change in force over change in x. It goes up 60 newtons in the 0.5 meters that I'm working over. And so what's the slope? Well, 60 divided by 0.5 is 120, and then we have newtons over meters, and so that's our unit. So what's the slope of this graph? It's 120 newtons per meter. And by the way, just real quick, if you look at this equation up here, what do you get if you take force divided by displacement? It is the spring constant. And yes, I dropped the negative sign because it only indicates that the two vectors are on opposite sides. So what's this number down here? It's the spring constant for whatever spring we're using. All right. Good luck with the homework. Let us know if you have any problems, and we'll see you soon. Bye.